Okay, hi everybody. This is a recording for chapter 14, right, in the textbook, chapter 14. Chapter 14 is all about the frequency response. This is the last bit of tooling we need, and pretty much before we can go back and start looking at negative feedback systems again. Okay, so I jumped over chapter 13. You probably realized that chapter 13 is an optional chapter. It's not going to be graded on, but it sort of explains the origins of the Laplace transform and also how it came from the Fourier transform and then in turn from the Fourier series. So it turns out to be really useful. In fact, the Fourier transform is the thing that's really useful for working out a frequency response. So what do I mean by frequency response? You've probably done this already in a previous class to some degree, but let's go over it again anyway. So let's say you have a system with transfer function h of s, okay? Let's say you have a system with transfer function h of s. We apply an input, we get an output, right? We've seen that before. The inputs can be step inputs, ramps, impulses, including sine waves, okay? Now, so I can put in a sine wave. Here's a sine wave, and out comes another sine wave. So since the system is linear, because you've obviously got a transform for it, so it must be linear. One of the characteristics of injecting a sine wave into a system is that the system will output a sine wave of the same frequency as the sine wave you injected into the system. So if I have a sine wave here, omega t, omega is the frequency or angular frequency. What comes out is another sine wave, right? But with a different amplitude, and it now has a phase, right? So there's no phase here, okay? But now it actually comes out with a phase. Note the frequency has stayed the same, or the angular frequency has stayed the same, okay? So a linear system, all right, we'll just summarize this here. Linear system, omega stays same, amplitude changes, phase changes, okay? Right, that's the important thing to note. Frequency stays the same, amplitude changes, phase changes, right? That's what this linear system will do, right? Now, it'll also do it to varying degrees depending on the actual frequency of the sine wave coming in, right? And that's what's of interest here. And that's what we mean by frequency response. How does the system respond to particular frequencies for the sine wave? How are the amplitudes and the phases changed as the frequency is changed? So you can imagine in an experiment, you'd inject a circuit with an input of a given frequency. You look at the sine wave that comes out, look at its amplitude, look at its phase, you'd record those, and then you try a new frequency and do the same thing, right? You can do this many times. And if you do that, you end up with what we call Bode plots, okay? Bode plots from the person called Bode who invented them or introduced them. So there's two Bode plots, one for the amplitude, one for the phase, right? One for the amplitude, one for the phase. The x-axis is always logged, and it's either the log of the angular frequency or the log of the frequency in hertz, okay? It doesn't matter which one really. Depends on your application, but the x-axis is always logged. The y-axis on the amplitude is also logged, and it's logged by just re-expressing the amplitude change in terms of decibels, okay? Which is a log scale. So those of you who do into music might be familiar with decibels in terms of the output from an amplifier or something. So the y-axis is always in decibels. The phase, the y-axis always, pretty much always degrees. I've never seen it in radians. It's always degrees. And since we start off with a phase of 0, it usually starts, right at the lowest frequency, it usually starts at 0. We'll come back to what this point is on the amplitude plot towards the end. Now, for a first order system like this, or a single tank of water, or a single capacitor and resistor. These are all what are called first order systems. And they usually have a particular behavior in the frequency response. This is basically what it looks like. So if you look at the amplitude, this is what it looks like. It sort of decreases rather slowly and then suddenly increases. Okay. This decrease here is actually very rapid because we're on a log scale here. So this is basically exponentially dropping. So once it starts losing the amplitude at higher frequencies. So remember, this is at higher frequencies. Okay, these are high frequencies here, low frequencies here. All right, so at very high frequencies, the amplitude drops. And you can imagine that because, I mean, I guess if you had let's say a reaction system like this with a production and a consumption and a production, and you injected a sine wave into the input, right? Of course, X has to fill up and empty, and the speed at which that happens is determined by the rate constants here. Okay, now if the sine wave is very slow, right, then presumably X can keep up. All right, and what you see is a fairly accurate reflection of the sine wave that's actually coming in. Right, now as the frequency, if you start turning up the frequency, X finds it more and more difficult to keep up, right? Because it can only go so fast in filling and emptying, because that's dictated by the rate constants. And so you start to see amplitude changes, usually a drop, right, and a phase shift. Okay. And this is basically what you're seeing here. So at high frequencies, the system just simply cannot keep up with the higher frequency. On the phase starts to lag, okay, because it takes time for X to rise and fall, right? So it tends to lag, and then you see the frequency drop. And what's interesting is the frequency drops to an asymptote. Actually, it doesn't keep on dropping forever. It actually stops dropping. In fact, it stops dropping at minus 90 degrees. The maximum phase shift you get, no matter how high the frequency, is minus 90 degrees. Now note that at these high frequencies, of course, the amplitude that's coming out is really tiny. And I'll do a demo shortly to show you that kind of thing in action. All right, so so these are the body plots. The question is, how do you compute them? Right, so how do you compute body plots? There's a couple of ways. One, you can do it algebraically. Okay, and the way you do it algebraically, you have your transfer function, h of s, and you literally multiply it by an input, which is a sine function, okay? And you'll get out x of s, right? Now that you can do that, and I give an example in the textbook, and it's instructive to follow through that, but it's a bit awkward because for a sine wave, q of s is as s squared plus omega squared. All right, so it's you have to multiply that then into your h of s. All right, and that becomes rather awkward. I mean, you don't want to do that really. And for anything non-trivial, you're not going to do it that way. A better way of doing it though is through the Laplace transform. What you can actually do is this. So if you remember that S, the Laplace transform S is sigma plus omega. This sigma is the real component, and that was added to the Laplace transform to give it better convergent properties when you do the integration. And this allows the Laplace transform to apply to many more functions. Now, without the sigma, we end up with just j omega, and this then becomes the Fourier transform. All right. Now, once you're in the Fourier transform space, you're sort of closer to the sines and cosines that are represented by the Fourier series, and it turns out that it's actually quite straightforward to work out the frequency response using the Fourier transform. And the way we do that is quite straightforward. You take your transfer function and you basically re-express it in terms of JWs instead of H's. So let's do an example, right? Let's think of, let's think of the simplest example, which is a first order system, right? So I want to know what the frequency response is for a first order system. So instead of having to go through all this multiplication business here, right, I can actually now just set S to I j omega. So I get H j omega equals 1 over j omega plus A. Okay. Now, you probably realize now that this number here that's computed here is now a complex number. Okay. And of course, complex numbers have phase and amplitude. And these are actually the phase and amplitude of the frequency response. Now, if you remember, a complex number can be plotted in an Argand diagram where the y-axis is the imaginary and the x-axis is the real. So if I had, say, the complex number a plus bj, I would represent that as a vector on this diagram where the coordinates are, the real part is there and the imaginary part is there. Okay. Now the phase, we can now that we've got in this diagrammatic form, we can talk about things like the phase, which is that, or the amplitude, which is basically the length of the vector. Okay. So this complex number here will have these properties. Now you can see here, this doesn't look like a plus bj, does it? So first thing you have to do is convert that. Okay, so when you have a situation like this, where you need to try and convert it into the standard form. So this is called the standard form. The way to do it is to multiply top and bottom by the conjugate of the complex number. So the complex number is the denominator, okay? So I somehow need to move it into the numerator. So what I do is, pink, I don't want pink. What I do is this. So another conjugate, oops, the conjugate is just, actually, let me do it this way. We swap those around. I'm basically following what's in the textbook, okay? So the conjugate, of course, is a minus j omega, and I multiply top and bottom by them both. So I haven't changed anything effectively, right? But now you see I have that multiplication. And when you multiply two conjugate complex numbers, you eliminate the real parts. Sorry, you eliminate the imaginary parts. These bits basically disappear because you get j squared, which turns into -1, and then the ja and ajw add up to nothing, so they disappear. So the complex number completely disappears. So what I end up then with is a over a squared plus omega squared, right, minus j omega over a squared plus omega squared. Okay, so this denominator comes from this bit here, right, and then the numerator portion you can see is split between the a and the j omega. So now you can see it's in the form I want. So this is effectively the real part. Okay, then this piece here is the imaginary part. Okay, so I have it, right? Now, once I have it in this form, I can compute the phase and the amplitude. Amplitude is the easiest one because it's just the length of that vector. And we just use Pythagoras' theorem on this triangle, okay, on this triangle, which is just basically a squared plus b squared, square root of. So the amplitude then becomes, it's the square root of a squared plus b squared, right? Which is square root of this one, the real part, a over a squared plus omega squared, plus omega squared. Oops, no, hold on, I got to must remember to square the whole thing. Forgetting that, square the whole thing. And then that's a squared plus omega squared all square. This actually simplifies quite a bit, and we end up with 1 over square root of a squared plus omega squared. Okay. Now, so that's the amplitude. Now, of course, you can see that this value is maximal when the frequency is 0. Okay. As the frequency increases, however, this ratio drops. So that matches what we saw in the Bode plot. Okay. So it drops, all right? So as the frequency goes up, it drops. And that's reflected in this one, this equation. Now, what about the phase? Well, the phase is this angle here, okay? And you work out your trigonometry. It involves arctan. So the phase equals tan to the -1. This is just trigonometry now, okay? Minus omega over a, okay? Which equals minus tan. I can take the minus out. Omega over a, all right? Now, if you remember, or you may not remember what the arctan looks like, arctan is, oops, go away. Yes, so if I plot the arctan, okay, tan -1, so x along here, okay, I will get something that looks like that, okay. This hits, and since we're taking the if you're doing it in degrees at least anyway, the y-axis then is in degrees, and this is actually 90 degrees, okay, and it's down here then is minus 90 degrees, right? Okay, so that's the maximum value tan minus h gets. Now that happens at high x or very negative x, okay. Oops, I should put it up here, I guess. Very negative x, and so that's why it didn't matter whether I had the minus there or here. If omega is very high, right, that means this ratio is high, so we're up here somewhere, okay, we're up here somewhere, and that means that this value then is negative, is 90 degrees, but the negative sign gives it minus 90 degrees, okay. So at high omega, right, theta tends to minus 90 degrees, okay, and this is what we see here, okay, so it tends to minus 90 degrees, okay. All right, okay, let me check my notes, see what's next. Yeah, okay. All right, the other thing I want to point out is a little bit about decibels. So the amplitude is log of omega, which could be radians per second or hertz. Up here then is decibels. The decibels are defined as, where is it? Oh, because I've forgotten. Oh, here it is. It is 20 log 10 and then the amplitude, okay, whatever the amplitude is, right? Actually, let me get rid of those. I don't need those bars there. Whatever the amplitude is, okay. So that's how you can compute the decibels. So if you've got a value of 100, that becomes 2 times 20 is 40, so the decibel is 40. Now, a couple of rules of thumb. Okay, a couple of rules of thumb. If we double the amplitude, then decibel goes up 6 dB, okay? If we times 40 the amplitude, then decibel goes up by 20. Okay, so this gives you some feel for the numbers. The most important one, though, is the bandwidth. Okay, the bandwidth. So let me draw one of these here, okay? And I'm going to draw Bodhi plot does that, okay? So this is going to be log omega, and this is decibels here, okay? Now, if the amplitude drops to say about to 70% of the maximum, right? So this is 70% of the maximum, okay? Then where this intersects, this is called the bandwidth. So this is the frequency for the bandwidth, all right? Another way of thinking about it is that in terms of dB, this has dropped 3 dB, okay? This has dropped 3 dB, all right? So when people talk about, the bandwidth for an amplifier, what they mean is, the sound, basically the sound pretty much maintains its frequency over a fairly wideish range. Sorry, the sound maintains its amplitude over a fairly wide range of frequencies, right? And there's a cutoff here, 70% or 3 dB, where, after that, it just pretty much drops off pretty rapidly. So within this range, amplifier can reasonably reproduce the sound loudness across all these frequencies. But after that, you start losing the sound, right? And that's because the electronic circuits in the amplifier simply can't keep up with the changing frequencies. Okay. Okay. So that's the bandwidth. What I want to do now is I'm going to switch to the computer. I want to show you some software, okay? And I want to show you something. So let me just stop sharing my tablet, and then I'll just go and share my screen. Okay, let's minimize that, Okay, so here I've got Spider running Python, all right? Hopefully you can see it. I've imported a bunch of stuff. I've imported Theorem, which is the modeling platform. I've imported SciPy, in particular Signal from SciPy. I've imported matplotlib. I've imported NumPy, the array library, and I've imported math. Do I need? I think I need math for one thing. Yeah, I needed to access pi actually. Okay, so what this does is, and I'm going to clear this so you don't I don't want to spoil the fun before it happens. But what I've got here is a linear chain, right? I've got an input here, x0. I'm going to designate that the input. That gets converted to x1, right? And the dollar means that it's fixed, okay? So I have control over the input. Gets converted to x1, x1 gets converted to x2, x2 gets converted to x3, and then finally x3 just gets converted to waste effectively. I have first order kinetics on every one of them, and I've initialized some values here. Okay. Now, the signal method, maybe I should bring it up. Let's bring up a new window. Let's have a look at this SciPy signal. There it is. Okay, SciPy signal. Here we go. If you look at this, what you'll see down here is what I'm looking for is LTI. Yeah, where's LTI? There it is. Continuous time linear systems. LTI is a function that lets me specify a system. Okay. And there are different ways to specify the system. You can literally specify it by writing down the poles and zeros. Okay. All right, I think that's what this one's doing. Okay, yeah, the poles and zeros. The other one, where is it? Ooh, yeah. Oh yeah. So okay, let me step back here. 3 ways of specifying a system: as a transfer function, as zeros and poles, and the gain, or as a state space. So if you have the zeros and poles and the gain, right, the big K, you can specify them directly here. And of course, there will be multiple zeros and multiple poles, so you put those in an array. The other way is to actually specify the coefficients. Let's say you don't have the poles or zeros, but what you do have is the characteristic equation, and you have the polynomial in the numerator. You can specify the coefficients, okay, for the 2 polynomials, all right? The only thing you got to make sure is that's in standard form for this to work. The other way is to specify the linear time invariant matrices themselves, A, B, C, and D, okay? And that's what I'm going to do here, okay? So remember, A was the Jacobian, B was the control matrix, okay? So we're not worried about C and D, but I have to set them up, but I'll show you that in a minute. So if you're using Tellurium, you can pick up the Jacobian directly, all right? So the first thing I'm going to do though is compute the steady state, right? So you do all these analyses around steady state, all right? Okay, so I'm going to compute the steady state for this system. I'm going to ask it for the Jacobian. Okay, that's A. Now B is going to be, if you remember B, so A, I'm going to write over here, A was an n by n matrix. Okay, n is the number of state variables. B is an n by p matrix, where p is the number of inputs. I've only got one input here, okay? So B will be and I've only got I've got 3 state variables though. It'll be 3 by 1, okay? All right, so here we have it as 3 by 1, okay? Now the RK, of course, the entries in the B matrix are, of course, dx by dt by d, whatever my input is, all right? My input is going to be x0. And since x0 only appears in the differential equation involving x1, and if I differentiate that with respect to x0, I just get k1. So I end up with k1 here, okay? The other differential equations, x2 and x3, don't contain x1, so I have zeros for all those entries, all right? The D matrix, I'm not interested in the D matrix, I just set it to 0. The C matrix, though, is the output matrix. This is how the state variables are transmitted to the outputs, the Ys, okay, which we haven't talked about much, but basically we're going to do a one-to-one transformation. So basically the value of the state variable is going to be the same as the output, okay? Now to do that, I did find that a little bit weird in this toolkit, but if I want the x value, the first x value, I put a 1 there, right? So that basically lets the output for x1 through. If I wanted to look at the output for the second variable, I have to put a 1 there. And if I want to look at the output for the third variable, I'll put a 1 there. Okay. So, but I'm going to put an input. I'm going to look at x1 basically. Okay, which is that one there. All right. Here I'm just specifying a log space for the frequencies. All right. Okay, and I'm converting it into frequency. Actually, I'm converting it into angular frequency. Okay. And this gives me orders of magnitude, right? So it's from 10 to the minus 4 to 10 to the 3. Okay. And it's going to be a log scale, right? All right. Once I've done that, then I just call signal.lti with the 4 matrices A, B, C, and D, and I get this variable back called sys. I can do all sorts of things for sys. One of the things I can do is ask it to compute the Bode data for that system. So I have to pass it the sys variable and the my range of frequencies over which I'm going to look at. Okay. Then here I'm just setting up the plot. I'm setting up the amplitude plot. And making sure the x-axis is logged, right? Now it looks like I didn't check this, but it looks like the magnitude. So it returns 3 variables, okay? The frequency, the amplitude, actually, and the phase. And it looks like the amplitude is already logged, okay? Because I don't have to log the y-axis. This is something you might want to look up in the documentation. I'm putting on a grid to make it look nice, then I show the graph. For the phase, I do the same thing. This time passing in the phase instead, make the grid and show it again, okay? All right, so we're basically done. That's all you have to do a Bode plot. You can do the same thing in MATLAB, all right? The nice thing here is I've hooked up our simulator, Theorem, up to the signal system, so I can get the frequency response for any reaction system I want, actually. Okay, so let's run this. It complains a bit here, but the answers are correct, so I guess we'll ignore that. And here you see the result. So this is the amplitude one, and that's the phase shift. And you see the phase is shifting from 0, starts at 0, okay, at low frequency, and then dives down to minus 90. That's basically minus 90 degrees, all right? The bandwidth is somewhere around here, okay, between these 2 markers. And this basically is the same as a first order system. In fact, it's a first order because I'm looking at x1. All right, so that's basically the first entry in this chain. Now the second entry basically behaves as a second order, and the third entry behaves as a third. Sorry, the second entry behaves as a second order, and the third entry behaves as a third order. So if I switch off the first one and switch on x2, let's have a look at that. And here we have again. Notice the amplitude falls off more for x2. You can't, perhaps if I move this up a bit, you can see that it falls off and it goes down quicker. At least the fall off is quicker. Okay. What's more interesting though for us actually is that the phase shift goes down to, this is actually minus 180 degrees. In fact, it's shifted by another 90 degrees. So a first order system shifts by minus 90 degrees. A second order system shifts by 180. I think you can imagine what will happen if I now select X3, which is equivalent to looking at a third order system. And here we go. Look at that, minus 270. So the phase shift for the third order system has added another minus 90 degrees and is now shifting by minus 270. Okay. In fact, if you put in another one, X4 species, you could shift by another 90 degrees. In fact, you come full circle and you're back in phase. Okay. Bear in mind, however, that at these high frequencies, the amplitude will be very, very small. Okay. Which takes me to the next thing I want to do. So what I want to do now is actually do a simulation to show you this in action. So I'm going to have a simple first order system. Okay. There's a mistake there, fix that. Okay, and then I'm going to set up some random rate constants. Okay, set x0 say to 0, and then what I want to do is I want to compute. Let me see. No, I want to do that. Let's run this now for first. Okay, straight line. That's because I should have set that up to something. Okay, I have a response. Let's increase this to 60. That takes me up to 60 on here. Okay, that's better. Basically, I want to get to steady state. That looks like a 5 maybe. So I'll set x to 5 and then run it again. Yeah, it's pretty much 5. Okay. All right, so we're at steady state. So what I'm going to do now is I'm going to inject a sine wave into the system. All right. Let's see. Actually, let me reduce this to 1. I'm going to reduce that to 1. It's going to make things easier for me. Let me hold on for a minute. That's probably gone down to 0.5, I guess. Yeah. Okay. So I'm going to inject a sine wave. The way you do that is actually quite simple. You just go x0 become. You have to use the colon equal symbol, a sine wave. And I can put in time as an argument. Okay. I have to get rid of the x here, otherwise it'll complain. If I run this, see, I get a sine wave. Now you notice though that's dropping below 0 because of course the sine wave goes from -1 to +1. So I need to, I'm going to increase it by 2 so that the middle portion of the sine wave is actually at 1. Actually, no, I wanted to go up by 1.5 so that I hit the steady state level of 0.5. So if I do this, that's not quite right. Is it? Maybe I have to go up. Oh, maybe I go up by 1. Yeah. Yeah, that's it. Yeah, I have to go by 1, of course. So here's my sine wave. Okay, there's my sine wave. Looking good. You can see it's a bit jaggy, so I'll increase the number of data points, okay, to make it smooth it out a bit. And there you go. Okay. Now that is X actually. That's actually what X is looking like. I'm going to plot all 3 here, x0 and x. Okay. All right, so x is a bit on the small side. You can see that's the. Let me what I want to do here. I want to see if I change the frequency here a bit. Yeah, okay, that's much lower frequency. And you notice that the amplitude increased a bit. Well, it has, yeah, it has increased a little bit, right? So it's going from just about 0.5 up to about almost 1, whereas up here it went from 0.5 to about 0.6. So at lower frequencies, you can see the amplitude of X is higher. The other thing you may notice is you see the phase shift here. You see the X. The peak for X doesn't match the peak in X and 0. That's the phase shift, okay? Now, if you look up here, you also see a phase shift, but it's not so clear there. But if I try, let me try and increase the frequency a lot more. Yeah, that didn't really help, did it? Yeah, I need to reduce the time now. Let me reduce the time. Reduce the time more further, because I want to show you that, yeah, it might be hard to tell. In fact, what I'm going to do is I'm going to create another variable, X scaled, where I'm going to multiply X by 10 just to make it bigger so we can see. It's difficult to see the phase shift here, right? Because the amplitude has dropped so much. Let me run it, and then I'm going to plot XS. So this is going to be 10. I'm just going to scale it up. That's all. Yeah, except then it does that to it. So let me try that. Okay, there we are. It may be probably difficult to see, but let me not decrease it so much. Okay, all right, here we go. The phase has actually shifted almost 90 degrees. Okay, so from peak to peak is 360, right? From peak to the bottom peak is 180. From the peak to the middle is 90. So you can see that it's almost hitting the 90. So this peak of the peak of the orange is almost 90 degrees ahead of the peak for X0. All right. And that's as far as it'll move. If I increase the frequency further, it won't shift much more, because the problem becomes the amplitude gets smaller and smaller. I mean, it becomes difficult to see. Let me see what that looks like. Yeah, you can see it now here. So there's the peak, the blue one, and there you see the orange one peaking at above 90 degrees. It won't shift further to the right because the maximum phase shift is minus 90. Okay. All right. So come Tuesday, we'll do more experiments like this. Okay. So bring in your laptops. All right, I'm going to switch back now to the tablet. Okay, and I want to do one last thing, which is an important topic. A little bit of magic you can do when you're working in the frequency domain, on the Laplace domain. It's called the final. Oops, no, sorry. What am I talking about? We've done that final value theorem. No. What I want to talk about now, sorry about that. I want to ask the question, what is that H of 0? Right, so if we're putting in the frequency here, that means at 0 frequency. What is the response at 0 frequency? So when I plotted this is particularly interesting when it comes to the amplitude. When I plotted the amplitude, right, I got that. Okay, so this is the amplitude plot. And I want to know what is this intersection point? What is that? That's basically, I mean, if you extrapolate it all the way back, okay, eventually it hits 0, right? At least approaching 0 anyway. So the question is, what is that? That's what I want to answer. Okay. All right. So I'm going to have a system. Let's have a system H of S. Okay. And I'm going to apply a step input to it. So I'm going to have an input called X0, and I'm going to apply a step input, right? In the Laplace transform, okay, so that step input is delta X0. In the Laplace domain, that's delta X0 over S, okay? So this is the response to a step input delta X, okay? All right. Now, what is the value of X? Or rather, yeah, here, what is the what is the value of x, x at steady state after I've done this step input? Well, the way to work out that out, of course, is to use the final value theorem. This is why I was confused with the final value theorem. So I can use the final value theorem here. Remember, this was used to compute steady state directly from the transform without going via the time domain. So in other words, I have to apply the final value theorem to this thing. So that means I go y lim, s goes to 0, s delta x 0 over s h of s, okay? And this equals the steady state value for x. Now, because I did a delta x, I'm basically looking at the change in the steady state value of x, okay? All right, so that cancels, that turns into 0. So I end up with delta x 0, h of x 0 equals delta x ss. Now I can rearrange this to give me delta x ss over delta x 0. Now in the limit, as I make the change smaller and smaller, which I would do in reality, that becomes dxss over dx0. Okay. So this is a derivative. In fact, this is a derivative. This, in fact, is a sensitivity. This is the sensitivity of the steady state with respect to the input. All right. So this value here, this intersection here, is actually dx by dx0. All right. And we'll come back to that in the future. So that gives us an interpretation for H0. It's just the sensitivity of the system, steady state level of the system with respect to the input. Okay. All right. And that completes it. All right. That's completes it. We'll do an example of this in class then to show that this is indeed the case for simple systems. Okay. We're done. And I'm going to upload this.